Example 5A11. A step drum having mass of M and radius of gyration about its center O of KO is attached to a smooth shaft passing through its center O. A cable wrapped around the outer radius of the drum is attached to block A. The second cable is wrapped around the inner radius of the drum, with this cable pulled over an ideal pulley and is attached to block B. Assume that the cables do not slip on the drum. The system is released from rest. Determine the angular acceleration of the drum on release. Write your answer as a vector. And we are given MA equals 10 kilograms, MB equals 30 kilograms, M equals 20 kilograms, R equals 0.2 meters, R equals 0.4 meters, and KO equals 0.25 meters.
With this information, we can complete step 1, which is drawing a free body diagram. We'll need one for each body. This is the free body diagram of body M, and you can see the reaction forces at O, the tension in cable B, A, and you can also see the mass center weight force. And then these are all the forces on A and B. And step 2 is to make a coordinate system. So we're going to use I and J. Next, we can move on to step 3, where we write all the forces in vector form. Next, we can move on to step 4, where we write acceleration at mass center in vector form.
For body A, we'll have acceleration of AG equals AG, or acceleration of AG scalar in the J direction, because it's only moving up or down. And the same thing for mass body B. And for mass body C, we will have the acceleration equal to 0I and 0J, which could just also be written as 0. For step 5, we're going to apply the F equals ma equation, and we will start with body A, and we will, on the left-hand side, add up all the forces of body A, and then on the left-hand side, the mass times the acceleration of A. And that is for, the acceleration is for the center of mass of A. And that'll be our first scalar equation. And then for mass body B, we will do the same process, which will look pretty similar. And then for mass body C, we know the acceleration equals 0. So we can add up the I terms and set those equal to 0, and then add up the J terms and set those equal to 0. And that gives us two more scalar equations. And for step 6, we're going to apply the sum of the moments formula. And we are going to use this formula for the wheel mass. And we are going to put point O on point G, which is the center of mass, and that'll cancel out the second part, or the second term on the right-hand side of the equation. So we'll just be left with the sum of the moment. The sum of the moments equals the mass moment of inertia about O times the angular acceleration. And we know the mass moment of inertia about O is the mass of the disk times the radius of gyration squared. So we'll do the moments, and TA will create a positive moment, and TB will create a negative moment. And we'll set that equal to our mass moment of inertia times angular acceleration. And then from that, we can get another scalar equation, because these are all in the k direction. And for our final step here, since we need a few more equations, scalar equations, that is, we will use some kinematic equations, and we'll do the acceleration about A and compare that to the acceleration of O, which we know to be 0. And we will and point A is going to be the point of contact between the rope attaching A and the outer radius of the disk. So the acceleration of that point will be equal to the acceleration of A itself. And then we can simplify that down to another scalar equation. And we can do the same thing for the point where the rope attaching B to the drum is, and find the acceleration of that point, which will be equal to the acceleration of the mass B. And then we'll use the same equation except with small r, since that's where the rope B is attached. And that'll give us our 7th scalar equation. From there, we can plug in equations 6 and 7 to our equations 1 and 2. And from there, we will plug in what we got for TA and TB into equation 5. And from there, that'll simplify to, with a whole lot of simple algebra that we're not going to take the time to go through. For this, we could get our angular acceleration. And then plugging in our values, that should give us a quantifiable number for the angular acceleration. And we made sure to write that in vector notation as the problem requests. And that is all. That's completion of the problem.